Okay, so we're going to take a look at an angular momentum question. And in this one, they give us the mass, position, velocities, and applied forces of 3 particles. So we have 3 objects in space here, but they aren't connected in any way. So we got 3 independent objects. First question that they're asking us here is to find the total angular momentum due to the 3 particles about the origin. And then the second part is determine the rate of change of the angular momentum. So for the first part, if you want to find the total angular momentum due to 3 particles, we can just calculate the angular momentum of each particle individually and then add them all up at the end. So the equation off the handout here that we're going to take is angular momentum is equal to the position crossed with the linear momentum. So first thing we're going to need is linear momentum of all 3 of these particles. So let's start with that. So the equation for that's just going to be mass times velocity. Everything's in base units here, so I'm just going to drop my units until the end. And then we'll just do the same thing for the second one and the third one. Okay, so that'll give us 20 kilogram meters per second in the I-hat direction. Oh, this should be I-hat as well. Okay, and then the last one, linear momentum of object 3 will be the mass 3 times velocity 3. So that will be 1 times 3 I-hat. Okay, so now that we've got that, we can do our cross product here. So L1 equals R1 cross with P1. So I usually set these ones up like this. There's a couple different ways to do the cross product here. Okay, now if we do our cross product, you'll see that most of these are just going to cancel out because of all the zeros that we've got here. There's only going to be one non-zero term, and that'll be in the positive k-hat direction. Okay, so now that we've got that for the first one, we can go ahead and do the same thing for the second and third ones. So we're just going to be doing 2 more cross products here. And so for the position, we had 4 meters in the I-hat and 1 in the j-hat. And for the linear momentum of this one, we had 20 in the x. So we do our cross product again. You'll see again, most of these are going to be 0, except for negative k-hat this time. Okay, so we get minus 20 for angular momentum of particle 2. So now we just got to do the last one. Okay, so for the position of 3, we had 2 and minus 2. and the angular momentum was just 3. So same as last time, we're just going to get negative k hat direction for this one. Okay, so now that we've got the angular momentum for each particle, we can find the total angular momentum. So for that, all we're going to do is add up all those different angular momentums that we just calculated. So for that first one, we had minus 16. The second one, we had minus 20. And the third one, we had plus 6. And so that's just going to give us minus 30. Good. And that's the answer for the first part here, is what is the total angular momentum about the origin? We can just take the angular momentum of each particle, calculate that individually. We know the position, we know the speed, we know the mass, so we can figure out that. And then once we have those for each particle, we can just add them together. Okay, now for the second part, we want to find the rate of change of the angular momentum. So there's another equation off our formula sheet that we're going to need here. So let me just pull that one out first. So the change in our angular momentum, that's going to be equal to the sum of torques. We also know that the sum of torques is going to be the sum of those forces times those distances. So in vector format, what that's going to look like is, we'll write it like this. We'll say we got the perpendicular distance cross product with the force. So before we start calculating things, let's just figure out these perpendicular distances. So if we look at force 1, that one's going in negative I hat direction. So that means that the perpendicular distance for object 1 that we're interested in is just going to be 1 meter in the j hat. For force number 2, that one has a force going in the y direction. So that means that the perpendicular distance that we're interested in for that one is just going to be the x direction. So it's just the opposite of what's happening in the force. If we had a force that was more complicated, it had x and y components, we'd have to do a bit more work. But since our forces are just in the x or just in the y, it makes it a little bit easier. And then for particle 3, again, force is in the y, so we're going to take the x direction. Okay, so now we can say, okay, torque number 1, that's going to be R1 perpendicular cross with force number 1. And these cross products will be pretty easy. So for R1 perpendicular, we just have 1 in the y. And for that force, we just had minus 6 in the x. So when we do that cross product, we're just going to get 1 times minus 6 times negative k hat. So we'll get 6 Newton meters k hat for that first one. And then we can just repeat the same thing for the other ones. So for torque number 2, that's going to be perpendicular distance cross with that force. for that one, we had 4 in the x and 0 in everything else. And 10 for that force in the y. So for that one, we're just going to get 4 times 10 in the k-hat direction, so it's going to be 40 Newton meters. Okay, last one here. Torque number 3. So for that one, it's going to be 2, 0, 0, 2, 0. And then minus 8 for the force in the y. Okay, and then we do that cross product. We're going to get our torque number 3 here as 2 times minus 8 in the k-hat direction. So that's going to be minus 60 Newton meters. Okay, now we can figure out the sum of our torques. So we can just add those up together. So if we do that, we had 6 plus 40 minus 16. So that means that our sum of our torques is going to be 30 Newton meters, k-hat. But we also said that the change in angular momentum is going to be equal to the sum of torques. So our change in angular momentum will also be 30 Newton meters, k-hat. And so that would be the final answer for that one. So for this question, we just went through how to come up with total angular momentum of independent particles. So for that one, you could just add them all up individually. And then same thing for change of rate of angular momentum. First thing we need to realize is that the change in our angular momentum with respect to time, that's going to be the same thing as the sum of our torques. So probably the easiest way to go about that one is just calculate all your torques and then add them all up.